Hello student, welcome to my channel The Learn Physics. Today I will be discussing the one short video of work, energy and power. Now our discussions are the definition of dot product and different properties and one related numerical with dot product. Then the notions of work energy theorem, that is work done by all forces is equal to change of kinetic energy, and two related numericals. Then work done is equal to dot product of force vector and displacement vector and two related Ncert numerical. Then work done by the variable forces, and to clear your concept, three Ncert numericals. Then work energy theorem by variable forces. Here potential energy due to position and due to shape, conservation of mechanical energy, conservative force, non-conservative force, power and collisions, both head-on collision as well as oblique collisions. Look at this, and Ncert numerical corresponding these topics. So after watching this video, your concept becomes clear and you can solve all types of numerical or multiple concept of the work, energy, power. Okay, now let's start. Now first of all, scalar product of two vector. Look at this. Suppose a vector is equal to x1 I cap plus y1 j cap plus z1 k cap, and b vector is equal to, this is the x2 I cap plus y2 j cap plus z2 k cap. Now we have to calculate the dot product of a vector and b vector. Now look at this, the dot product of a vector and b vector is the modulus of a modulus of b into cos theta, where theta is the angle between the two vectors. Look at this is the a vector and this is the b vector, okay, and this is the angle theta. Now look at this. Now if a perpendicular is drawn on it, now this represents b cos theta. So look at this, the dot product of a vector and b vector is magnitude of a and projection of b on a. Understood? Magnitude of a into projection of b on a. Okay, now special cases. When theta equal to 0 degree, when theta equal to 0 degree, look at this, a vector dot b vector, this equal to ab. That is I vector, that is I cap dot I cap equal to 1 cos 0 degree equal to 1, that is j dot j equal to k dot k. Okay, understood? Now when theta equal to 90 degree, look at this, a vector dot b vector, this equal to 0, because cos 90 equal to 0, that is 0. Therefore from this condition, I dot j equal to j dot k equal to k dot I is also 0. Okay, now look at this, the a vector dot b vector equal to 0 is called conditions of perpendicularity. Okay, now angle between the two vector. Look at this, the angle between the two vector, from this relation we can get, look at this, this is the a vector dot b vector divided by magnitude of a and b. Okay, understood? Now we have to calculate a dot b in terms of x1 x2 y1 y2 z1 z2. Look at this, here a vector dot b vector. Now we have to calculate the a vector dot b vector in terms of x1 x2 y1 y2 z1 z2. Look at this, here a vector dot b vector, this equal to x1 I cap plus y1 j cap plus z1 k cap. Okay, dot, this is the x2 I cap plus y2 j cap plus j2 k cap. Look at this. We know I dot I equal to 1, j dot j equal to 1 and k dot k equal to 1. And I dot j 0, j dot k 0, k dot I 0. So look at this. Only this that is x1 x2 plus this y1 y2 and finally this that is z1 z2 are the results. So a vector dot b vector, this is equal to, look at this, x1 x2 plus y1 y2 plus z1 z2. Okay, understood? Next, now look at this Ncert example 6.1. Look at this. Here force vector and displacement vectors are given. We have to calculate angle between the two vectors and projection of F on D, that is displacement. Now we have to calculate theta and F cos theta. Okay, now look at this. Look at this, the cos theta is equal to, look at this here, F vector dot D vector divided by magnitude of F into magnitude of D. Now look at this, what is F dot D? Look at this, 3 into 5, 15, 4 into 4, 16, minus 5 into minus 3, 15. So look at this is the 3 into 5 plus minus 4 plus 5 into 3. Okay. Now this divide by, look at this, magnitude of this. Look at this is the 3 square plus 4 square plus minus of 5 square. So 3 square plus 4 square plus minus 5 whole square. And again look at this is the 5 square plus 4 square plus minus 3 whole square. So look at this is the 15 plus 16, this is the 15 divided by, look at this is the root over 50 into this is the root over 50. Okay, this is the 46 by 50. So this is the 23 by 25. Okay, therefore theta equal to cos inverse of 23 by 25. Okay, now next the projection of F on D, that is F cos theta. Look at this, F cos theta means magnitude of F. Look at this magnitude of F, this is the root 50 and cos theta, that is 23 by 25. So look at this is the 5 root 2 into 23 by 25. So look at this 20 root. So here this is the 23 root 2 by 5 is the projection of F on D. Okay, understood? Now we have to establish the relation of work done and change of kinetic energy, that is the work energy theorem. Suppose a particle of mass m moves with velocity u. A force F acts on it to change its velocity from u to v. In this duration, if the distance traveled by the particle is s, then we can write from the kinematics v square equal to u square plus 2as. So look at this here, s equals to, this is the v square minus u square by 2a. Therefore work done equal to F into s, that is equal to, this is the mass into acceleration into displacement. So look at this is the mass into acceleration and this is the v square minus u square by 2ic. Now a cancel out, therefore work done F into s, this is the half mv square minus half mu square. So work done by the force is equal to change of kinetic energy. This is known as work energy theorem. Now this can be written as work done by all external forces is equal to change of kinetic energy. Okay, now numerical. Now example 6.2. Now a raindrop is falling from height of 1 kilometer in a. Now a raindrop of mass 1 gram is falling from the height of 1 kilometer. Final velocity before reaching the ground is 50 meters per second. We have to calculate work done by the gravity and work done by the resistive force. Now work done by the gravity. Look at this, the work done by the gravity is the mgh. So look at this here, m is the 1 into 10 to the power minus 3 kg, g is the 10 and h is the 1000. Okay, so this is the 10 joule. Okay, now final kinetic energy. Look at this, the final kinetic energy K equal to half mv square. Look at this here, half mass is the 1 into 10 to the power minus 3 and v is the 50 whole square. So look at this is the half into 10 to the power minus 3 and this is the 2500. So look at this is the 1.25 joule. Now if we apply the work energy theorem, the work done by all forces is equal to change of kinetic energy. So work done by gravity plus work done by resistive force is equal to change of kinetic energy, that is delta K. Now work done by the gravity, this is the work done by the gravity is the 10 joule plus work done by unknown forces equal to change of kinetic energy, that is 125 joule. Therefore work done by unknown forces, this is the 1.25 minus 10, that is minus 8.75 joule. Okay, understood? Next, now look at this is a block of mass 2 kg is pulled by a horizontal force 7 Newton. The force of friction acting on this direction. Now we have to calculate work done by this force, work done by force of friction, work done by the net force and change of kinetic energy. First of all, we have to calculate displacement in 10 seconds. So look at this here, acceleration A equal to, this is the net force by mass. Now net force 7 minus mu n, so this is the mu 1 and n is equal to, look at this, n equal to 20 Newton, so this is the 20 Newton by mass 2 kg. So look at this is the 7 minus 2 by 2, so this is the 2.5 meter per second square. So displacement S equal to, look at this is the half a t square. So here half a is the 2.5 and t is the 10 square. So look at this is the 50. So this is the 50 into 2.5, that is 125 meter. Now look at this, work done by the force F. Look at this, F equal to 7 Newton. So this is 7 into 125, that is 875 joule. Okay, now work done by force of friction. Look at this, the force of friction is equal to this. So force of friction 0.1 into 20, that is 2 Newton. So look at this is the 2 into 125, that is 250 joule. Okay, now work done by net force. Look at this is the 7 Newton and this is the 2 Newton. So net force is 5 Newton. So look at this is the 5 into 125, this is the 625 joule. Now we have to calculate change of kinetic energy. Here velocity v equal to, look at 0 plus a into t. A is the 2.5, so this is the 2.5 into 10, so this is the 25. Okay, now the change of kinetic energy, this is the half m, mass is the 2 and v is the 25 whole square, so this is the 625 joule. Look at this here, work done by net force is equal to change of kinetic energy. Okay, understood? Now next, now work. If a force F is acting on a particle produces displacement S vector, then work done W equal to, this is the force vector dot displacement vector. It also can be represented, this is the S vector dot F vector. Now therefore W equal to Fs cos theta, where theta is the angle between the F vector and displacement vector. Now when theta equal to 0 degree, when theta equal to 0 degree, that is displacement is in the direction of applied force. Here work done, look at this, here work done F W equal to, here work done W equal to F into S. This is called positive work or work done by the force. Okay, when theta equal to, this is the 180 degree, that is work done equal to Fs minus 1. So this is called negative work, okay, or work done against the force. Look at this, if a ball falls from a height, the work done by the gravity is positive. If a body is projected vertically upward, during its upward motion, work done by the gravity is negative. Okay, now when theta equal to 90 degree, that is force vector is perpendicular to displacement vector. Here work done is equal to 0. Look at this, here work done is equal to 0. The force acting in this case is called no work force. Centripetal force always acting normal to the direction of velocity. That is why centripetal force is called the no work force. Okay, the earth revolves around the sun in a circular path. The gravitational force of attraction in this case acts as a centripetal force. So here gravitational force is no work force, as no work done by the gravitational force during a revolution of earth around the sun. Okay, next, Ncert example 6.3. A cyclist comes to a skidding stop in 10 meters. In this case, the opposing force acting by the rod is 200 Newton. Now we have to calculate work done by the rod on cyclist and work done by the cyclist on the road. Okay, now look at this, here work done by the rod on the cyclist. Look at this, here opposing force, this is the 200. Look at this, here opposing force 200 Newton and displacement 10 meter. So look at this is the 2000 joule is the work done. Now as there is no displacement occurs on the road, so work done by the cyclist is equal to 0. Okay, understood? Next, now Ncert is 6.11. A body is restricted to move along z axis by the force minus I cap plus 2j cap plus 3k cap Newton. We have to calculate work done. Now we know the work done is equal to F vector dot S vector. Here force vector given, so this is the minus I cap plus 2j cap plus 3k cap dot, this is the 4k cap. Okay, now look at this, this is the, look at this, now this is the this 0, this 0, but this and this one, so this is the 12 joule is the work done by the force. Okay, now there is other units to express the work done. Look at this, 1 arc 10 to the power minus 7 joule, 1 calorie, this is the 4.2 joule, 1 kilowatt hour is equal to 3.6 into 10 to the power 6 joule. Okay, and 1 EV, this is the 1.6 into 10 to the power minus 19 joule. Okay, understood? Remember this. Now we have to establish the relation between momentum and kinetic energy of a body. If a body moves with velocity v, if a body of mass m moves with velocity v, then its momentum small p equal to, this is the mv, and its kinetic energy k equal to, this is the half m v vector dot v vector, so this is the half m v square. Now here v equal to, this is the p by m, So from this relation we get k equal to, this is the half m, this is the p by m whole square. So look at this is the k equal to, this is the p square by 2m, is the relation between kinetic energy and momentum. Now here momentum can also be expressed as p equal to root under 2me. Okay, for a very small percentage, look at this, for very small percentage change of momentum, the change of kinetic energy is, look at this, delta k by k, this is the 2 delta p by p. That is, if momentum increased by 1%, then kinetic energy increased by 2 into 1%, that is 2%. If momentum increased by 5%, then kinetic energy increased by 10%. For larger percentage such as 50%, 200%, this formula is not obeyed. This obeyed for very small change. Look at this, if momentum is increased by 100%, then we have to calculate the increment of kinetic energy. Suppose initial momentum is p and initial kinetic energy is k. So look at this, here k equal to, this is the p square by 2m, this is relation number 1. If momentum is increased by 1%, then look at this, the final momentum p dash, this equal to p plus 100% of p. Okay, that is p plus 100 by 100 into p, that is the 2p. So look at this, the kinetic energy k dash, this is the p dash square by 2m. So look at this, this is the 2p by, so this is the 2p whole square divided by 2m. So this is the 4 into p square by 2m, that is, this is the 4k. Okay, so final kinetic energy becomes the 4 times of initial kinetic energy, that is, this is the 400% of k. So kinetic energy increased by 300%. So kinetic energy increased by 400 minus 100, that is 300%. Okay, understood? Next. Now next question, if kinetic energy increased by 96%, then find the increment of momentum. Now look at this, suppose initial momentum is p and initial kinetic energy is k. So look at this, here p equal to root over 2mk. Okay, now kinetic energy increased by 96%, that is k dash equal to k plus 96% of k. Okay, understood? Now look at this, here k plus 96 by 100 into k. So look at this, this is the 1.96k. Okay, now we have to calculate p dash. Now p dash equals to, look at this is the 2m k dash. Therefore, this is the 2m into 1.96k. So look at this, under root of 1.96, that is 1.4. So look at this is the 1.4, this is the 2mk. So this is the 1.4p, that is 140% of p. Therefore, the momentum is increased by 140 minus 100, that is 40%. Okay, understood? Next, look at this, work done by the variable forces. Suppose a force is like this. Okay, now we have to calculate work done by these forces. Now look at this, for this variable force, for very small displacement dx is taken here. So this is the dx. Now look at this, the work done for very small displacement dx is equal to f into dx, and this f dx represents the area of the shaded portion. Therefore, work done from x equal to x1 to x equal to x2 is integration of, look at this, this is the x1 to x2 f dot dx. Okay, the integration of x1 to x2 f dx represents the area under the graph, area under fx graph. So work done by the variable force is the work done under the fs graph. Okay, understood? Next. And now Ncert numerical 6.5. Now a woman pushes a trunk by applying force 100 Newton for 10 meter. Then she decreases forces uniformly from 100 Newton to 50 Newton and finally displaces the 10 meter. Here force of friction is 50 Newton. We have to plot the Fs and Fs graph and work done by the F1 and F2 and work done by the force of friction. Now this is the displacement, okay, and this is the applied force. Look at this, here force is acting 100 Newton along this direction and displace the 10 meter, okay, this is the 10 meter. Then she decreases the force uniformly and displace another 10 meter, okay, here 50, okay. Now the force of friction in throughout the path, this is the minus 50 Newton, okay. Now we have to calculate work done. We know the area under Fs graph represents the work done. So work done by F1 and F2 is the area of this person plus area of this person. So look at this, work done by forces. This equal to area of this person. This is the 100 and this is the 10. So this is the 100 into 10. Now this area is the area of the trapezium. This is the 100, this is the 50. So look at this, this is the 100 plus 50 divided by 2 into 10, okay. So this is the 1000 plus this is the 750. So work done is 1750 joule. Now work done by the force of friction, look at this area. So this is the work done by force of friction is equal to minus 50 into 20. This is the minus 1000 joule, okay. Understood? Next. Now Ncert example 6.6. A mass of 1 kg moves with velocity 2 meter per second enter into a rough surface ranging from 0.1 meter to 2.01 meter and resistive force is minus k by x. Now we have to calculate the final velocity. Now from work energy theorem we know that the change of kinetic energy half mvf square minus half mvi square, this equal to work done by the forces. Here work done by the variable forces. So work done by the variable forces, this is the F into dx from this is the 0.1 to 2.01, okay. Now look at this, this is the half m common 1, so this is the vf square minus 2 square, this equal to, look at this, this is the minus k, this is the dx by x, this is the 0.1 to 2.01. Now look at this, here vf square minus 4, this is the minus 2k into, look at this, this is the ln 2.01 by 0.1. Now here ln 20.0, this is the 3. So look at this, this is the minus 2 into k into 3. So look at this, minus 2, k is the 0.5. Look at this, k is the 0.5. So look at this, this is the 3, this is the minus 3. So look at this, vf square, this is the 4 minus 3, this is the 1. Therefore vf equal to 1. So final velocity becomes 1 meter per second, okay. Next. Now Ncert 6.20. A particle of mass 0.1 kg moves with velocity 5 into x to the power 3 by 2. We have to calculate work done during the displacement x equals to 0 to x equals to 2 meter. Okay. Now first of all we have to calculate acceleration, then force. Now look at this, here v is equal to 5x to the power 3 by 2. Now differentiating v with respect to x, so dv by dx, this is the 5 into 3 by 2 into x to the power 3 by 2 minus 1, okay. So look at this. This is the 15 by 2. This is the x to the power half. Now acceleration a equal to v dv by dx. Look at this. Here v equal to this. So here 5 into x to the power 3 by 2. v by dx equals to 5 by 2 x to the power half. Okay. So look at this. This is the 75 by 2 and this is the x square. Okay. Understood? So force F equal to, look at this, force F equal to, this is the mass into acceleration. Mass is the 0.5 and acceleration is the 5 by 2 into x square. So look at this. This is the 70. Look at this here, 75 by 4. This is the x square. Therefore, work done by this force during displacement 0 to 2 meter is equal to, look at this equal to f dx. This is the 0 to 2. Now f is equal to, look at this, 75 by 4 and this is the x square dx and this is the 0 to 2. So this is the 75 by 4 and this is the x cube by 3 and this limit 0 to 2. This equal to 75 by 4 into 3 into 2 cube minus 0 cube. Okay. Now this and this cancel out, 25, and this is the 8 into 25 by 4. This and this cancel out 2. So this is the 50 joule is the work done. Okay. So work done by the variable force during the displacement x is to 0 to x is to 2 meter is 50 joule. Okay. Next, look at this. Suppose this is a closed path. If work done by a force in this closed path is equal to 0, then this force is called conservative force. For a conservative force, look at this, work done F delta x, this equal to change of kinetic energy. And for a conservative system, look at this, F into dx, this is the minus potential energy. Okay, now change of kinetic energy equal to negative sign of change of potential energy. Now look at this, here delta k plus delta v equal to 0. So delta equals to k plus v equal to 0. That is kinetic energy plus potential energy equal to constant. This principle is known as conservation of mechanical energy. So for a conservative system, the sum of potential energy plus kinetic energy is equal to constant. Okay. Now non-conservative system. The system where mechanical energy is not conserved is called non-conservative system, such as rough surface. And work done by the non-conservative force in a closed path is not 0. Okay. Next. Now Ncert is 6.7. A particle of mass m is suspended by means of a string of length L. It is projected with velocity v0 at A in such a way that it completes semicircular path, and at the top point the string becomes slack. We have to calculate the velocity at B, velocity at C, and ratio of kinetic energy at B and C. And what happens, the motion of the particle after the point C. Okay. Now look at this, as the string becomes slack at the point C. So look at this, here tension Tc equal to 0, or at mg acting vertically downward direction, and centrifugal force m Vc square by L is directed radially outward. So now in this case, for equilibrium of the body, this is the m Vc square by L equal to mg. Therefore Vc equal to root under gl. Okay. Now we have to calculate Vo and Vb. Now from conservation of mechanical energy, look at this, the change of kinetic energy half m v0 square minus half m vc square. Look at this equal to change of potential energy. Now from this position, now the distance between this, now the vertical distance of A and C is the 2L. So change of potential energy is mg into 2L. So this is the mg into 2L. Now here this is the v naught square minus vc square. This is the 4gl. Now v naught square, this equal to vc square plus 4gl. Look at this, vc equal to root under gl. So this is the gl plus 4gl, that is this is the 5gl. So vo equals to root under of 5gl. Okay, now we have to calculate the velocity Vv. Look at this, again applying the conservation of mechanical energy. Look at this, half m v naught square minus half m Vv square. This is distance between this and this is L. So this is the mg into L. So here v naught square minus Vv square, this is the 2gl. Now v naught square is equal to 5gl. So look at this, here Vb square. So here Vb square is equal to 5gl minus 2gl, that is 3gl. Therefore Vb equal to root under of 3gl. Okay. Now we have to calculate the ratio of kinetic energy at B and at C. Look at this is the half m, this is the Vv square by half m, this is the Vc square. Look at this cancel out. So this is the Vb by Vc. So Vv square by Vc square. This is the 3gl by gl. So this is the 3. Okay. Now last question. What happens the motion of the particle after C? Look at this. After C, the motion of the particle remain in the circular path. If the string is cut, then it executes the projectile motion from a height. Okay. Now work energy theorem for variable forces. Now look at this, kinetic energy K is equal to half mv square, where m is the mass of the body moving with velocity v. Now differentiating with respect to t, so dk by dt is equal to half m into d dt of v square. Okay, so this is the half m into 2v dv by dt. Now we know dv by dt is equal to acceleration. Here 2 and 2 cancel. So this is the m into a into v equal to dk by dt. Okay. Now dk by dt is equal to force into dv means dx by dt. Now dt and dt cancel out. So look at this, here dk equal to, this is the f dx. Now integrating this equation, okay, when x equals to x1, kinetic energy k equal to k1. When x equals to x2, kinetic energy k equal to k2. Okay, therefore look at this, here k2 minus k1 equal to integration x1 to x2, here f into dx. This is the work energy theorem for variable forces. Now a numerical. A force of F equal to minus 8x Newton acting on a particle of mass 2 kg. Moving with velocity of 10 meter per second at x equals to 0. Find velocity of the particle at x equals to 3 meter. Mass of the particle is equal to 2 kg. Now to solve this numerical, we have to apply the work energy theorem for variable forces. Now look at this. Here half mv square minus u square, this equal to work done by variable force, that is here x1 to x2. Now look at this, this is the half, m is the 2, v square, means we have to calculate it, and this is the 10 square, this is the minus 8 x dx from 0 to 3. Okay, understood? Now look at this cancel out. So v square minus 100, this equals to minus 8, and this is the x square by 2 integration 3 to 0. Now this and this cancel out. So look at this. So here v square equal to 100 minus 36, that is 64, that is 8 square. Therefore v equal to 8. Therefore velocity of the particle is 8 meter per second at x equals to 3 meter. Okay, next. Now potential energy. The energy possessed by particle due to its configuration, position and shape is called potential energy. Now potential energy of position. Suppose a particle of mass m is raised to a height h. So the force acting on the particle of mass m is mg in the downward direction. So work done by an agent to move from this position to height h is W equal to mgh. Therefore potential energy of the body due to its position at a height h is mgh. Now the potential energy above the earth's surface or a reference level is positive, and potential energy below the earth's surface or below the reference level is negative. Okay, now potential energy due to shape. Suppose a force F acting at the lower end of a spring which is fixed at its upper end. If x means elongation, then F equal to kx. Therefore this force is a variable force. So here work done by this force due to elongation x is equal to integration f dx from 0 to x. And this is the kx dx from integration 0 to x. So this is the half kx square. Therefore energy stored due to its position is half kx square. Now x equals to f by k. So look at this, here half k into f by k whole square. So this is the f square by 2k is the energy stored in the spring. Okay, understood? Now next. Now Ncert numerical 6.27. A lift rises with velocity 7 meter per second and a bolt at the ceiling of the lift falls from this position to the ground. We have to calculate heat energy produced. Will heat energy different if the lift is stationary? Now we give the answer at the last part. Look at this, the relative velocity of the bolt with respect to the lift is 0 when it moves with 7 meter per second or it's stationary. That is why heat produced equal to mgh is always same. Now heat produced h equal to mgh. Here mass is equal to 0.3, g is the 10 meter per second square and h is the 3. So this is the 9 joule. Okay, so heat produced is 9 joule. Okay, next. Now in a typical simulation, a car of mass 100 kg moves with velocity 18 km per hour, collides with a spring system whose force constant is 6.25 into 10 to the power 3 Newton per meter. We have to calculate the maximum compression. Now here kinetic energy of the car is converted into elastic potential energy. So look at this. This is the half kx square elastic potential energy equal to kinetic energy of the car. Now this and this cancel out. So look at this, k is the 6.25 into 10 to the power 3 x square and this is the 1000 kg into v square, that is 5 square. Look at this and this cancel out. So x square equal to 25 by this is the 6.25, this is the 4. Therefore x equals to 2. Therefore maximum compression of the spring system is 2 meter. Okay. Now look at this. the graph of potential energy and x is given here. Look at this here, potential energy 0, that is the potential is converted into kinetic energy. Now here potential energy is maximum. Now we have to prove the maximum potential energy equal to 1 joule when x equals to 2 meter. Now put the value. So here V2 is equal to half k. K is the 0.5, x is the 2. Okay, so look at this is the 1 by 2 into half into 4. So this is the 1 joule. So maximum potential energy is equal to 1 joule at x equals to 2 meter or x equals to minus 2 meter. Okay, next. Now Ncert is 6.26. Look at this. This is a horizontal spring of force constant 100 Newton per meter. Now it is connected with a load, it is connected with a block of mass 1 kg. Now when the block is released, the block moves down by a distance of 10 centimeter. So elongation of the spring is 10 centimeter. Now we have to calculate the coefficient of friction between the block and the plane. Now in this case, the energy stored in a spring is equal to work done by gravity along the inclined plane and work done by force of friction. Look at this, the work done by the gravity, this becomes mg sin theta into s. Work done by force of friction, this is the minus f into s, that is minus mu mg cos theta into s. So energy stored in the spring half k a square, this is the mg sin theta into s minus mu mg cos theta into s. So 1 s is cancelled out. So look at this, this is the half k s, this is the mg sin theta minus mu mg cos theta. Okay, now look at this, this is the half, k is the 100, s is the 0.1 and this is the 1 kg, this is the 10 and this is the 3 by 5 minus this is the mu into, look at this, 1 into 10 into 4 by 5. Okay, now look at this, this is the 5. Okay, equal to, look at this, this is the 6 and minus this is the 8 mu. So look at this here, 8 mu is equal to 6 minus 5. So mu equals to 1 by 8. Therefore 0.125. Okay. So coefficient of friction is 0.125. Okay. Understood? Next. Now power. Power is the rate of work done. Look at this, power P equal to, this is the work done by time. Now work done is the force into displacement by time. Now S by T is the V, so force into velocity. In vector form, power equals to force vector dot velocity vector. Okay? The unit of power is watt. More unit used to indicate power, such as 1 arc per second is equal to 10 to the power minus 7 watt. Okay, now 1 HP, this is equal to 746 watt. Okay, now look at this example 6.11. A lift of mass 1800 kg moves up with 2 meter per second. Resistive force is equal to 400 Newton. We have to calculate power required for its motion. Now look at this, here forces F equal to, this is the mg plus F. Now here m is the 1800 into 10 plus 4000. Okay, so look at this, this is the 18,000 plus 4000. So this is the 22,000 is the force acting in downward direction. Now power P equal to force into velocity. So this is the 22000 into 2. This is the watt. Now if we express, so this is the 400 watt. Now this can be converted into HP. So it should be divided by 746. So this is the 44000 by 746 HP. This almost equals to 59 HP. Okay, understood? Next. Now look at this. A particle initially at rest, it moves with constant acceleration. How power related to time? Now we know power P equal to, this is the force into velocity. Now look at this force. So this is the force into, now we know here V equal to U plus AT. Now here U0, so this is the AT. So here V equal to AT. Okay. Now here P equal to force, mass into acceleration into AT. So look, so this is the M into A square into T. This is constant. So power directly proportional to time T. Okay. A particle moves with constant power. How? S depends on time. Okay. Power P equal to, this is the force into velocity. Now force equal to mass into acceleration into V. Now here acceleration is equal to dV by dt into V. Here V dV equal to P by M into dt. Now integrating both sides. Look at this. When time t 0, the velocity 0. Now when time t, the velocity v. So look at this. This is the v square by 2 and this is the p by m into t. Therefore v equal to root under 2p by m into t to the power half. Okay. Now we know v equal to ds by dt. So look at this. Here ds by dt is equal to root over 2p by m into t to the power half. So ds equals to root under of 2p by m t to the power half dt. Okay. Now integrating this equation. Look at this. When t equal to 0, s 0. When t equal to t, s is s. Okay. So look at this. Here s minus 0. This is the 2p by m and this is the t to the power 3 by 2 divided by 3 by 2. So look at this. S equals to 2 by 3 root under of 2p by m t to the power, this is the 3 by 2. So displacement directly proportional to t to the power 3 by 2. Okay. Understood? Next. Now Ncert 6.15. An electric pump raises 30 meter cube water to a height of 40 meter. In 15 minutes, we have to calculate the electrical power consumed if efficiency is 30%. Now look at this. So power P equal to, this is the work done by time. So here M is equal to, look at this, 30 into 100. So here 30 into, now M equal to 30 into 1000. So here 30 into 1000. G is the 10, H is the 40 and this is the 15 into 60 is the mechanical power used by the motor. So look at this and this is the 2. Okay. Now this and this is the 20. So look at this. Here this is the 3 and this is the 4. So look at this is the 4 into 10 to the power 4 divided by 3 watt. Now efficiency equal to output divided by input. Okay. Now we know the output. Output is this, we have to calculate input. Now input, that is the electrical power, is equal to, this is the 4 into 10 to the power 4 divided by 3 into 30%, that is 30 by 100. Okay. This and this cancel out. So look at this is the 40 into 10 to the power 4 divided by 9. So look at this is the 4.4 into 10 to the power 4 watt. So 44 kilowatt is the electrical power consumed by the motor. Okay. The wind strikes the blade of a windmill of area 30 meters square. We have to calculate the electrical power generated if the efficiency is 25%. Now here rate of wind energy. Look at this is the half dm by dt into v square. So look at this is the electrical power. Now look at this, dm by dt, this is equal to a v into rho. So look at this here, half into a into v into rho into v square. So look at this is the half rho a, this is the v cube. We know the efficiency equal to output by input. Here input is the wind power, output is the electrical power. So look at this, the electrical power divided by wind power, that is half rho a v cube, this is the 25%. So look at this, the electrical power P dash, this is the 1 by 8 rho a v cube. Now this is the 1 by 8, rho is the 1.2, a is the 30 and v is the 10 meter per second. So this is the 10 cube. Okay, this is the 36 by 8 into 10 to the power cube. So look at this is the 4.5 into 10 to the power cube watt, that is 4.5 kilowatt. Okay, so electrical power generated from the windmill is 4.5 kilowatt. Okay, understood? Next, now look at this, Ncert is 6.25. Two inclined plane meets at the point A. Here angle of inclination 30 degree and here 60 degree. Two stones are allowed to slide from the two inclined plane. We have to calculate the speed at the bottom of the inclined plane and time taken by the stone to reach the bottom. So first of all we have to calculate the velocity at the bottom point. Suppose this angle of inclination is theta. Suppose the length of the inclined plane is s. So look at this here, h by s, this equal to sine theta. Therefore s equals to h by sine theta. Okay, now we have to calculate velocity at this point. Here acceleration down the plane, this is the g sine theta. Okay, so look at this here, v with the velocity, then v square equal to 0 square plus 2 g sine theta into h by sine theta. So look at this, v equals to root under of 2gh. So velocity at the bottom of both the bodies are same, because the velocity at the bottom only depends on height of the inclined plane. Okay, here h equal to 10 meter, therefore v equals to root over 2 into 10 into 10. So this is the 10 root 2, that is almost 14 meter per second. So velocity at the bottom of both the bodies is 14 meter per second. Now we have to calculate the time of fall of these two bodies. Now if t be the time of fall, then look at this, h equal to half into g sine theta into t square. Now here s equals to h by sine theta. So look at this here, h by sine theta into half g sine theta into t square. So t equal to, look at this, 1 by sine theta into root under 2h by g. Look at this is the 1 by sine theta into root under 2 into 10 by 10. So t equal to, this is the 1. Look at this cancel out, so root 2, so this is the 1.4 by sine theta. Okay, this is the time of fall of the bodies. Now we have to calculate the time of fall of this body. Here theta equal to 30 degree, so t1 equal to 1.4 by sine, this is the 30 degree, so this is the 1.4 by half, so this is the 2.8 second. Okay, now we have to calculate the time of fall of this body. Here t2 equal to, this is the 1.4 by sine 60 degree. Okay, now look at this is the 1.4 divided by root 3 by 2. So look at this is the 2.8 by root 3 second. Okay, so this is the time of fall of this body and this is the time of fall of this body. Okay, understood? Now next, now elastic collision. the collision in which the linear momentum and linear kinetic energy of the colliding particle remains conserved. Suppose two bodies of mass m1 and m2 moves with velocity u1 and u2 in the same direction. So they collide. After collisions, their velocity becomes v1 and v2. So from definition we can write the conservation of linear momentum, that is initial momentum before collision is equal to final momentum after collision. Okay, understood? Okay, this is equation number 1. Now the conservation of linear kinetic energy. Look at this. The kinetic energy before collision, this is the half m1 u1 square plus half m2 u2 square equal to, this is the linear kinetic energy before collision of the colliding particle, and after the collision the linear kinetic energy, this is the half m1 v1 square plus half m2 v2 square. Okay, this equation is equation number 2. Okay, now from definition we can solve the Ncert numerical. Now look at this. This is 3 particles, 1, 2, 3. They collide elastically. Look at this. First particle collide elastically with 2 and 3 in contact. The final velocity, first is 0, second and third is v by 2. Now here in the second case, first and second are at rest, third moves with velocity v. In third case, 1, 2, 3 have velocity v by 3. We have to calculate which one is elastic collision. Now look at this. Here initial k, look at this. This is the k. Now this is the initial k, this is the half m v square. Now look at this here final k. Look at this here final k, half m plus m into v by 2 whole square. So look at this, this is the 1 by 2m into v square by 4. So look at this, this is the 1 by 4 m v square. So look at this here, initial energy half m v square, final energy 1 by 4 m v square. So this is not the elastic collision. Now look at this here, final kinetic energy, look at this here, only half m v square. So this is the elastic collision. Now look at this, in this case 3 have velocity v by 3. So look at this here, kinetic energy half into 3m into v by 3 whole square. So look at this, this is the 1 by 6 m v square. So this is not the elastic collision, because here initial kinetic energy half m v square, final is the 1 by 6 m v square. So only 2 are the elastic collision. So from definition we can solve this numerical. Okay, now there is another definition of elastic collision. Look, the collisions in which relative velocity of approach before collision is equal to relative velocity of their separation after collision. Now look at this, the relative velocity of approach before collision, this is the u1 minus u2, and relative velocity of separation after collision, this is the v2 minus v1. Okay, so look at this, this is the another relation of elastic collision. This is equation number 3. Now from equation 1 and equation 3 we can get, look at this, v1 is equal to, this is the m1 minus m2 divided by m1 plus m2 into u1 plus 2m2 u2 divided by m1 plus m2. v2 is obtained by interchanging m1 m2 and u1 u2. So look at this, v2 is the m2 minus m1 divided by m1 plus m2. Now this is the u1, so this becomes u2. Look at this here, this is the m2, so this is the m1, and u2 u1, and this is the m1 plus m2. Okay, these two relations are the final velocity of m1 and m2. Now special cases 1. Okay, if m1 equal to m2 equal to m, then look at this here, this is the 0, and this is the 2m by m plus m, so 2m by 2m, so this is the u2, therefore v1 is equal to u2. Similarly v2 equal to u1, therefore in elastic collision of two equal masses they exchange their velocity. Okay, now from this concept I can solve a Ncert numerical. Look at this, bob A and B of same mass m. The bob A released at an angle 30 degree and collides with B at rest. How high A will rise? Now look at this. Suppose when they collide, the velocity of A is, this is the u1. So look at this. This is the equal mass, this and this. The initial velocity of A before collision is u1 and initial velocity of B is u2 equal to 0. So in elastic collision between two equal masses, look at this, v1 equal to u2. So this body comes to rest and v2 is equal to u1 and this body moves with velocity u1. As this body will be at rest, so the no rise takes place of body A. Okay, understood? Next. Now special case 2. If u2 equal to 0 and m1 greater than m2, that is m1 plus m2 is equal to m1 and m1 minus m2, this also m1. So look at this here, v1, look at this here, m1 minus m2 by m1 plus m2, both m1 cancel out, so here v1 is equal to u1 and this is the 0. Now look at this here, this is the 0, so v2 becomes, look at this, v2 becomes 2m1 by m1, so this is the 2u1. So look at this, if elastic collision of heavy mass, now in elastic collision between a heavy mass and a stationary small mass, the small mass gets twice the velocity of heavy mass. Okay, now a numerical, this is the velocity u, it collides with this velocity whose mass is negligible in comparison to this, and finally this body collides with this body, this mass is negligible in comparison to, what is the velocity of this particle? And second question, if this body is not present, what is the velocity of this? Now look at this, if the body is present, then look at this, the velocity of this body u, so velocity of this body is 2u because its mass is negligible in comparison to this. This mass is negligible in comparison to, so this velocity is, this is the 2 into 2u, so this is the 4u. Okay, this mass is not present, so look at this body strikes this body, so this body has only velocity 2u because this is the large mass and this is the negligible mass. Okay, understood? Now special case 3, if m2 greater than m1 and u2 equal to 0. So look at this, m1 minus m2 equal to minus m2 and m1 plus m2, this is also m2. Now look at this here, v1, look at this here, v1 is equal to minus u1. Okay, and v2, look at this is the 0 and here 2m1 by m2, this fraction is negligibly small, so this is 0. Therefore in elastic collision between a moving small body and a stationary large body, the large body remain at stationary and the small body reflected back with the same velocity. Okay, understood? Now we have to calculate fractional transfer of energy from first body to second body. Consider the second body will be at rest. v2 becomes, look at this is the 0, so 0 plus this is the 2m1 into u1 divided by m1 plus m2. Look at this, the initial kinetic energy of second body is 0 and here final velocity of the second body is this. So kinetic energy of the second body this. So gain of kinetic energy is the final minus initial. Initial is 0. So this is the gain of kinetic energy. Now look at this. This is the half m2 into here 2 m1 u1 divided by m1 plus m2. This is whole square. So look at this. This is the half m1 u1 square, and this is the 4 m1 m2 divided by m1 plus m2. This is the whole square. Look at this. This is the initial kinetic energy of the first. So look at this. This is the E. Therefore delta E by E, this equal to, this is the 4 m1 m2 divided by m1 plus m2 whole square. Suppose m1 by m2 equal to k, or m2 by m1 is equal to k, then look at this. We can get delta E by E is equal to 4k divided by k plus 1 whole square. Look at this. If k equal to 1, delta E by E is equal to 1. Therefore fractional transfer of energy is 1, that is maximum. If k equal to 1, that is m1 equal to m2, that is the mass of the two bodies are equal. In nuclear reactor, deuterium is used to slow down the neutron. Now we have to calculate what fraction of kinetic energy will be reduced by the deuterium. Now look at this. The energy gained by, now the fraction of energy gained by deuterium. Look at this. This is the 4k divided by k plus 1 whole square. Now this by this is the 2. So look at this. 4 into 2 divided by 2 plus 1. This is the whole square. So this is the 8 by 9. So the 8 by 9 of whole energy of neutron is gained by deuterium. So energy remain in the neutron is 1 minus 8 by 9 of its initial energy, that is 1 by 9 of initial energy. Okay, understood? Next. Now the coefficient of restitution E. It is the ratio between relative velocity of separation of two particles after collision and relative velocity of approach of the two colliding particles before collision. Okay, so this is the V2 minus V1 divided by U1 minus U2. In case of elastic collision, look at this. This equal to this, so this ratio is equal to 1. So in case of elastic collision, E equal to 1. Okay, understood? Now inelastic collision, the collisions in which only linear momentum is conserved is called inelastic collision. Now look at this. Here initial momentum m1 u1 plus m2 u2, this equals to m1 v1 plus m2 v2. All natural collisions are false in this category. Okay, in inelastic collision, during collision sound energy, light energy, heat energy, etc. produced. So some portion of kinetic energy is dissipated. So dissipation of energy delta W, this is the half m1 m2 divided by m1 plus m2, and this is the u1 minus u2 whole square into 1 minus e square, where is the coefficient of restitution. In case of inelastic collision, E greater than equal to 0, less than 1. Okay, understood? Now perfectly inelastic collision, the collisions in which two colliding particles merge with each other, that is the two particles coalesce with each other. Therefore in this case here V1 equal to V2 equal to V. So in case of perfectly inelastic collision, initial momentum m1 u1 plus m2 u2 equal to m1 v plus m2v. So look at this, here v becomes, look at this is the m1u1 plus m2u2 divided by m1 plus m2. Now the coefficient of restitution in case of perfectly inelastic collision, look at this, here v1 equal to v2, so this numerator is 0, so look at this, E equal to 0. Therefore in case of perfectly inelastic collision, E equal to 0, therefore dissipation of energy, look at this becomes 0, so dissipation of energy becomes, this is the half m1 m2 divided by m1 plus m2 into u1 minus u2 whole square. Okay, look at this, a bullet of mass 0.01 kg moves with velocity 100 meter per second horizontally and strikes a block of mass 0.49 kg suspended horizontally by means of a string. The bullet embedded in it. The combined mass moves. We have to calculate the height ascended by the combined mass. Now look at this, as the bullet combined with the block, so it is the perfectly inelastic collision. Now in perfectly inelastic collision, this is the m1u1 plus m2u2 equal to m1 m2 into v. Okay, now look at this, this is the 0.01 into 100 plus this is the 0.49 into 0, this equals to 0.01 plus 0.49 and this is the v. Okay, so look at this is the 1 equal to 0.5 v, so here v equal to 2. Now kinetic energy of the combined mass at this position equal to potential energy at this position. So look at this is the half, this is the 0.5 into 2 square, this is equal to 0.5 into 10 into h. Okay, now look at this and this cancel out. So look at this, here 2 equal to 10h, therefore h is equal to 2 by 10, that is 0.2. So height ascended by the combined mass is 0.2 meter, that is 20 centimeter. Okay, understood? Now next. Now oblique collision. Look at this. Suppose a body of mass m1 moves with velocity u1, strikes obliquely with another body of mass m2 moves with velocity u2. So look at this is the line of propagation of the two. Now look at this, here this body, this is the m2 moves along this direction with velocity v2, and this is the, look at this, m1 moves with velocity v1. Okay, so if this angle is theta 2 and this angle is theta 1, now we have to consider the conservation of linear momentum along the line of motion and perpendicular to the line of motion. Now look at this, the initial momentum along the line of motion, this is the m1u1 plus m2u2. Now after collision, look at this, the component of this is the m1v1 cos theta 1 and this is the m2v2 cos theta 2, m2v2 cos theta 2. So here m1v1 cos theta 1 plus m2v2 cos theta 2. Again in normal direction, look at this is the m2v2 sin theta 2 and this is the m1v1 sin theta 1. So look at this, in normal direction m1v1 sin theta 1, this equal to m2v2 sin theta 2. Now if the collision is elastic, then conservation of linear kinetic energy takes place. So look at this is the half m1 u1 square plus half, this is the m2 u2 square, this equals to, this is the half m1 v1 square plus this is the half m2 v2 square. Now look at this, in case of oblique collision of two equal masses, the two bodies having mass m and m collides obliquely. The initial velocity of this is u and this is 0, and final velocity is here v1 and v2. Now from conservation of linear momentum we can write, look at this is the mu vector is equal to mv1 vector plus mv2 vector. Okay, now u vector is equal to v1 vector plus v2 vector. This is equation number 1. Now from conservation of linear kinetic energy we can write, this is the half mu square, this equal to half m v1 square plus half m, this is the v2 square. So look at this, u square equals to v1 square plus v2 square. This is equation 2. Now from this equation we can write u equal to root under of, look at this is the v1 square plus v2 square plus 2v1 v2 cos theta. It is the formula vector. Now from this condition we can write, look at this, u square equal to, this is the v1 square plus v2 square plus 2v1 v2 cos theta, where theta is the angle between the line of motion of the two particles. Now look at this, here v1 square plus v2 square, this is the u square. So look at this, u square equal to u square plus 2v1 v2 cos theta. Look at this and this cancel out, therefore cos theta equal to 0, so theta equal to 90 degree. Okay, understand? Therefore in oblique collision between two equal masses, the angle between line of motion after collision is 90 degree. Okay, understood? Now a numerical. This is the Q and this is the target. The Q hit the target and sent the target at an angle 37 degree, and the deflection of this with this direction. Look at this, as mass of two billiard balls are identical and elastic collision takes place between the two billiard balls. So look at this angle is 90 degree. Now this angle is 37 degree. This is the theta 1. So look at this, 37 degree plus theta 1. This is the 90 degree. So theta 1 is equal to 53 degree. Okay? Understood? Many thanks for watching this video. This video extremely helpful for class 11, NEET, main and advanced. Please like, share and comment on this and subscribe your channel to get the new concept in physics. Okay.